Hello and welcome to our project review video for our GE Non-Optical Flame Detection Algorithm project. We were Team 5 in the fall 2023 semester of ECE 4960, aka Senior Design 2. My name is Chandler No, and I worked on this project with Robert Anderson, James Bunton, and Emily McPherson. We had faculty help from Dr. Razza and Dr. Groff, and our GE help was Reese Taylor and Dr. Healy. So a brief introduction, we were working with GE Vernova's gas turbines, and they develop, produce, and sell these gas turbines for power generation. These are extremely powerful machines, and one of these could provide the electricity for many homes. These turbines have many sensors to detect key metrics, outputs, and any problems that may arise during operation. One of these problems is a loss of flame, aka LOF. A loss of flame is a safety critical issue and it must be detected 100% of the time. As you can imagine with how large these machines are and how powerful, they're going through a large amount of gas, and if this gas is not getting combusted properly, it can very quickly build up in a confined space and an explosion could easily happen. So in the field, these are detected with optical sensors. However, optical solutions do have some drawbacks, one of which being overheating and lens clouding. So this directly impacts the performance of the optical sensors. And because of this, you have to have many of them, which means you have to have redundancy, which of course means increasing the complexity of the turbine itself. So because of these problems, GE has been moving towards a purely sensor-based approach due to these issues. So that's where non-optical flame detection, aka NOFD, comes in. NOFD is done by reading in live data and signals from the onboard sensors. This data is then run through an algorithm that will detect binarily if a loss of flame happened or did not happen. So this algorithm has many constants, which would be things like thresholds, time delays, different derivatives to compare the signals to. And right now, the current algorithm is not used by itself in the field, and that is something that we were trying to help fix to make it accurate enough where it could be used by itself. So our task was to optimize and tune the algorithm by adjusting these constants that we discussed. So some key terms before we really get into the meat of the project. The margin value is essentially a confidence score that the algorithm assigns to a given case based on its reading. So it would assign its confidence that, oh hey, I said that the flame went out, this is how confident I am. The margin ID is an ID that indicates which signals are related to a failure, and these can be useful for diagnosing and figuring out which cases to target. A constant in this case is a constant within the GE NOFD algorithm itself, and these are thresholds, timings, and other various constraints as we discussed. A case is a set of sensor data from a certain turbine from a certain time. And when we say CLIMS in use, we are talking about a set of 22,000 cases that were designated for our use and don't include some of the weird edge cases or variances in the data. So mainly in this project, we were doing mathematical optimization, which is the process of maximizing or minimizing an objective function by finding the best possible set of values across a set of inputs. So that leads to the question, what is an objective function? Well, that is a function that is used to quantify the results of a problem into a single number. So for our implementation, the objective function was being minimized, and the input to it was a set of constants and a set of cases to be optimized, and the output was an aggregate margin. And as you remember, the margin is the confidence of the algorithm. So this is almost the collective confidence of the given case set with the constants we input. So our objective was to optimize GE's NOFD algorithm to improve the distribution of the margin values as much as possible, with specific focus on improving the margin values at the lower end of the distribution, aka the ones below 35, which is when it starts to become a dangerous margin value. And our motivation was to tackle a complex industry issue for GE, as well as build upon previous Clemson University students' work. So for our design, this is a purely software-based project, so there was really no hardware design. But our design had to build on an existing code base And on top of this code base, we had to create an objective function so we could evaluate our performance, a top level driver, which is where we'd be performing the optimizations, a data analysis suite where we could look at our data and interpret it, and some documentation, of course. And we were doing this using MATLAB Simulink and the Global Optimization Toolbox within MATLAB. So here's our block diagram for the semester, and this is essentially the process we were performing the entirety of the semester. And so basically every time we wanted to do an optimization, we would pick a certain algorithm from the global optimization toolbox. We would select cases and parameters. Then we would put that into MATLAB and that would run in tandem with the Simulink algorithm. And that would return a set of optimized data, aka the optimized constants. And so then from there, we would analyze how these constants perform against the entire Clemson use case set using our graphical analyzation tools. And then from there, we could see what was working, what kind of margin IDs were coming up, and we could refine our selections and repeat the process again. So as mentioned, the objective function is one of the most important parts of the project, and that is used to quantify the performance of a given set of constants. And so this would do this by aggregating the margin, which would use the formula in the bottom left there. And this was essentially how the optimization algorithms in the top level driver would know how well they're doing. They would evaluate their performance using this objective function, and then they would use whatever method they use to try a different set of values. So the main function of the project was the optimization driver. And this interfaced with the existing code base, which was the NOFD driver and its helper functions. And it was basically combining those with the optimization methods that were in the global optimization toolbox. And so this was essentially the hub for rerunning the Clemson use cases using optimized constants that we'd find and for running the optimizations in the first place. And this was what we spent the majority of our time working on and developing and running and looking at through this project. And so, as we mentioned, we need a data analysis in our design, and you can see some of the plots that we came up with to help evaluate our results. In the top right, you can see a plot that shows the margin IDs for a given set of cases. In this example, you can see the margin ID of 16, 26, and 53 look like the three IDs that have the most cases. And in this case set, we would be targeting those. And in the bottom right, you can see our margin versus margin graph, which compares the results of a run. So essentially, the x-axis is the initial margin value, and the y-axis is the final margin value of an optimization. And there's a line going down the middle of the graph, which is y equals x. Anything above that line means that the margin value went up after the optimization. Anything below means the margin value went down. And this was probably our most helpful tool when determining how well our optimizations were going. And we also had a couple other graphs to help look at the data throughout the year, but these weren't as helpful. So as we've talked about, the cases and the constants are the input to the objective function. So for our specific implementation, we were focusing on loss of flame cases within the Clemson use category that had a margin value between 0 and 35. And when you compare and contrast these, you're seeing three margin IDs that are the main causes of loss of flame, and that is margin ID 23, 53, and 84. And these correspond to these three signals, CDM time, CPD time, and TNH dot, respectively. And this is how we were able to determine which constants we were going to target. And the constants are listed there as well, to the right of the signal name. But these were the signals that we were mainly optimizing throughout the entirety of the year. So for our results, we actually saw better results than expected. So using the cases and constants that we just discussed, we did many rounds of optimization using pattern search on these cases and constants, and we were able to see the result of only two cases being brought down in the set to like a value that may become may start to be dangerous. We are able to half the number of cases between 0 and 35 from 420 to 210 through our optimizations. And a possible concern was that a few cases that were originally negative were decreased further, but however, these were ignored to get the results that we had because since they were already negative, it's possible that maybe these were just anomalies and these are not normal data. So our next steps would be to find a targeted way to efficiently deal with the remaining few cases in the set that are still being pulled down, and to look at the final margin ID distribution, and to further target these IDs that we see in the margin ID graph on the left here. So some challenges and bottlenecks through the semester. The main one would be coordinating meeting times. It's always hard to meet when you're remote and different locations have different schedules. Another problem was lab computer downtimes and issues, which we did experience, and that would limit our ability to log on and do optimizations and perform trial runs. And the final challenge would be, of course, learning a new set of tools. That's always difficult to come in and then jump right into learning a new set of new toolbox that you never used before, but that was another challenge that we had to overcome. And the main bottleneck was the fact that we were using one lab computer for the entirety of the semester. And because of this, we were only able to run one optimization at a time, and that severely limited our throughput and the availability of the lab machine itself. So in conclusion, we did not find a set of optimized constants that completely eliminated the loss of flame. However, we were able to develop a robust and mostly automated software infrastructure for running these optimizations, and we established a solid working process that we think future teams could use to continue and build on our results. And we were able to highlight some future directions for future teams. So some of these future directions, one of which would be to continue using pattern search optimization, which is what we landed on in the end. Another one could be to use a different optimization cycle within the global optimization toolbox, or perhaps implement some sort of hybrid method that utilizes multiple optimization algorithms. And then our main recommendation for a future direction would be to explore using the MATLAB Cloud or the Palmetto cluster at Clemson to increase the computational power of the program itself, because we were using 32 workers. If you could use 1,000 workers, it is very, very possible that you could get the work that took us a week done in a day. So that would be definitely a direction worth looking into for a future team. So here's our references, and I want to thank you for watching our video.